Hey everybody, today we're going to cover probability lesson number 3, and this is going to be more like the probability that you've already come to know. Probability meaning, the chance of something happening. We spent a lot of time in the last couple of lessons working through how many different ways something can happen. How many different ways can you choose from 3 shirts, 2 pairs of pants, and 4 pairs of shoes? Or, how many different ways can this drawing be done? Or how many different ways can you finish first, second, and third in a race with 8 people? You need that as your foundation, but now we're getting into what you're more familiar with, and in my opinion, it's more fun too. So we'll just go from there and see how we do. So, again, probability is the chance of something happening. So if you're watching a weather report and they say there's an 80% chance of snow, it is currently April, so I hope that's not the case, although that would not even be one of the 5 weirdest things that's happened this year. Anyway, if the scenario happened 5 times, there would be snow 4 of those times. So I want you to think of it in this case as 4 out of 5. Which then brings up the first thing I want you to know about probability is that you can write probability as a percent, 80% chance of snow. You could write it as a fraction, 4 out of 5, or you could write it as a decimal, which in this case would be 0.8. So all 3 of those would be a reasonable way of writing probability. If I don't tell you what way to write it, you can choose any of them. The key is a probability cannot be less than 0, and a probability cannot be greater than 1. So you can't have a negative 10% chance of something happening, and you can't have a 110% chance of something happening. So all the athletes who said, hey, I gave it 110% out there, they lied. Anyway, so the official definition of probability is the number of favorable outcomes divided by the number of total outcomes. So basically, let's say I wanted to roll the dice and I had to roll either a 5 or a 6. So that would mean, in this case, the number of total outcomes would be 6, because when you roll the dice, there are 6 things that could come up. And then out of those 6, I want to roll either a 5 or a 6, which means 2 of those 6 outcomes would be good for me. So the probability of getting what I want, the favorable outcome, would be 2 out of 6, which you could also write as 1/3 or 33% or all that good stuff. So, all right, let's get into when it gets a little bit more serious. We're going to start talking about compound probabilities. Now, compound probabilities are just like regular probabilities. Okay, but now we're talking about multiple parts. We're talking about, I'm going to roll 2 dice. I'm going to roll 1 die and I'm going to flip a coin. I'm going to do all these things together and then consider the probability of everything happening together. All right, now, type number 1, and this is actually a flashback to our first lesson. Type number 1 would be independent events. Now, these were the type of events where one event does not change the probability of the next event happening. So this would be, in case you don't get what I'm saying here, let's say you flip a coin 3 times. Each coin flip is separate, and the probability involved in a coin toss is separate each time. Just because you flipped the coin 3 times in a row and you got tails, let's say, that doesn't mean that the 4th time around it's going to be tails, or the 4th time around it's going to be heads. The probability doesn't change. It's 1/2 each time. So you have a 1 out of 2 probability of getting heads or getting tails every time you flip dice, and it doesn't matter if you got the same thing 10 times in a row. The 11th probability is still going to be 1 out of 2. So, what is the probability that you will flip a coin 3 times and land on heads all 3 times? Well, the probability the first time is 1/2. The probability the second time is 1/2. The probability the third time is 1/2. So the probability that it's going to happen all 3 times is going to be 1/2 times 1/2 times 1/2. All you have to do is just multiply each individual probability, which actually sounds a lot like the fundamental counting principle. If you remember when we did the 2 shirts, 3 pairs of pants, 2 pairs of shoes, all we did at the end was multiply the numbers and we had our final answer. Probability is exactly the same way. All you have to do is take the numbers, multiply them together, and you'll get your final result. So the probability that you will flip a coin 3 times and land on heads all 3 times is 1 out of 8. As a decimal, that would be 0.125. As a percent, that would be 12.5%. I don't really care which way you write it. I'm going to leave it as 1/8. All right, you must flip a coin twice and then roll 1 die. What is the probability that you will flip heads twice and then roll a 6? Again, we're talking about independent events, which means the probability is not going to change based on what happened before. So the probability of flipping a coin and getting heads the first time is 1/2. The second time is 1/2. And then you also have to roll a 6, which means on the dice there are 6 possible things that could happen, and you only want one of those options. The 6 is the only thing that you can get. So we're talking about a completely separate probability from the other 2. So you multiply, and 1 times 1 times 1 is, I don't know, maybe 1. And 2 times 2 times 6 is 24. So the probability that you are going to flip heads twice and roll a 6 is 1 out of 24. Now, if you were to take 1 out of 24, the other one I could do in my head, 1 out of 24, not so much, but it would be about 4.1%, give or take, if you were to, well, I'm sorry, it's 4.2%, I didn't round up. So that's not a very good probability. So the first one was 12.5%, the second one was 4.2%. All right, I rolled a die. Question number 3. I am thinking of a random letter and a random digit. What is the probability that you will guess both correctly? So a random letter and a random digit would be like if I was creating a code like H7 or Q5 or something like that. What is the probability that you will guess both correctly? Well, if I'm thinking of a random letter, you only have a 1 out of 26 chance of getting the letter that I am thinking of. Now, a random digit, there are 10 possibilities. Because remember, we're not talking about 1 through 9, we're talking about 0 through 9. And if you want to get my code right, you only have a 1 out of 10 chance of doing it. So that means the probability that you will guess both correctly, we are not looking good over here. This is 1 in 260. Now, as a decimal, if you were to take 1 divided by 260, you would find out that it's 0.0038, which would actually mean you have less than 1/2 of 1% chance of guessing my random letter and random digit correctly. So you actually, in case you forgot, when you move a decimal twice, you get a percent. So for instance, when you got your 0.0038, you have to move it once and then twice, and that becomes your percent. But we still didn't even make it past the 3. That means you have less than 1% chance of guessing correctly. All right, so now we are going to get into some code here. It's sort of just like a math code. What does it mean when you see the letter P and then parentheses and then stuff going on? So we're going to introduce a little bit of math code here. The first code is an intersection, and that's going to be that symbol that you see right there. Now, I don't want you to think too hard about this. Okay, you rolled 1 die and you flipped 1 coin. What is the probability of the intersection of even and. It just means and. When you see the probability of even and then that symbol and then heads, it just means and. Now, the probability of rolling a die and getting an even number is 3 out of 6. Okay, 3 out of 6 because you have 3 even numbers out of 6, so 3 out of 6, which if you wanted to just call that 1/2, it wouldn't be a big deal either way. Then the probability of flipping a coin and getting heads would be 1 out of 2. You've got 2 possible things that could happen. One of them would be you flipping a coin and getting heads. So really, if 3 over 6 is just the same as 1/2, then we're really just saying 1/2 times 1/2, right? And if you were to do 1/2 times 1/2, then you would get 1/4. So whenever you're talking about the probability of something and something else happening, all you have to do is multiply the probabilities, which is exactly what we have already been practicing. So when you see that symbol, there really isn't anything to it. Now, part B is going to be a little bit different. Part B here, whenever you see the U symbol, now you are talking about a union. Okay? So a union is sort of the equivalent of the word or. Okay. Now, I think the best way to explain this is actually with a Venn diagram. Okay. I know these are sort of something that you would see in different situations, sometimes not even math. Let's say we are talking about rolling an even number on the dice and flipping a coin and getting heads on top. So whenever you see one of those and problems, like our first example where you see the letter N, okay, it looks like kind of a upside down U. It's if you think of it like a letter N, then that sort of reminds you that it's an intersection. That symbol represents one event and the other one both happening. So that would be, if you're thinking about a Venn diagram, that would be this area in the middle. Whenever you see that symbol, that intersection symbol, that means one and the other. Now, whenever you see the union symbol, that would be that U right there. Again, that's going to be code for or, which means one or the other would be good. And technically, that also means if both happened, that would be good as well. Okay, so basically anything here or here or here would count toward the union. Okay, now this is where the Venn diagram really helps. To figure out the probability of one or the other happening, you have to figure out the probability of the first thing happening, then add the probability of the second thing happening, and then take away the repeat. You know, so basically, if you have two things happening and you want to know the probability of one or the other occurring, you could take each probability separately and add them up, but then you want to subtract off the repeat values. Okay, so let's talk about what that would look like here. In this case, we already have all of the numbers that we need from our first problem. We know that the probability of getting even is 1/2. We know the probability of flipping the coin and getting heads is 1/2. And we know that 1/4 of the time both are happening, and so we want to subtract away the repeated values because those are the ones that came up twice, and we don't want the ones that came up twice to be counted twice. So again, if both of them turn out to be true, then that means that value is being counted double, and we want to make sure that gets taken out. All right, so 1/2 plus 1/2 minus 1/4 would give you 3/4. Okay? So that is the official method for figuring out OR problems. That's a formula that's actually given to you on the end of course exam, which apparently is not relevant at the moment, so it's not really a big deal. All right, last thing, the probability, we've got this last scenario here. It's the probability of even, and then there's a line, and then heads. Now, that symbol essentially means given. As in, let's say we know that we flipped the coin and it came out heads. What is the probability of the dice coming out to an even number? So even given the fact that you already know that it's going to be heads. Now, that being said, if these events are independent, that symbol doesn't really matter. So again, the biggest key here is that if the events are independent, then it didn't really have anything to do with the other. I could tell you, hey, the coin came up tails. What is the probability of rolling an even number with the dice? Well, it's not like the die has eyes and is watching what the coin is doing. They are two completely separate entities, so they do separate things, and one event does not affect the other one. So whenever you see that symbol and you're talking about independent events, it doesn't actually change anything. There will be situations where it does, but we're going to get into that a little bit later. All right, type number 2. Now we're going to talk about dependent events. And this is where one event changes the probability of the next event happening. Okay, so watch what happens here. Watch why this problem is different. Your friend is holding 10 index cards numbered from 1 to 10. You draw a card, and without putting it back, you draw another card. What is the probability that both are even? So this is where it gets tricky. At first, you've got 10 cards to choose from, and 5 of them are even. But notice the biggest underlined keywords here. Without putting it back, you draw another card. What is the probability that both are even? So you did not put back the previous card, which means now you don't have 10 cards left to choose from. You have 9. Now, if that looks familiar, if that looks like something we were practicing in previous lessons where the number goes down by 1 every time, that's exactly why we were practicing it. It's so it all fits together. All right, now 9 of them are left, and of those 9, if you already picked an even the first time, that means there are only 4 even cards left the second time, which means the probability that both are even is going to be 5 times 4, which is 20. 10 times 9 is 90. And 20 over 90 actually reduces, and you could just call it 2 over 9. Easy enough. Now, as a percent, that would be 22%. We can practice our percents here on the back if we want to practice that. So, speaking of, let's turn to the back, and we're going to do just a few minutes of the back together. That way, you only have to do a couple problems here to wrap up. All right, find the probability of spinning a shaded region. So if you look on the spinner, there are 4 regions. 2 of them are shaded. 2 out of 4, which would be a probability of 1/2. And we'll practice our percents here as we go as well, so we'll call that 50%. All right, a factor of 27. A factor of 27 would be a number that goes into 27. So does 4 go into 27? Nope. Does 2 go into 27? Nope. Does 5 go into 27? Nope. The only one is 9. So if you think about kind of just a regular pie chart, out of the 4 options, only one of them is a factor of 27. So the probability of that happening would be 25%. All right, a number less than 6 or a shaded region. All right, so this is less than 6. This is less than 6. This is less than 6. This is not, but it is shaded, so it counts too. That means anything goes. That means the probability of spinning a number less than 6 or a shaded region is just 1, aka 100%. All right, an even number or a perfect square. So an even number or a perfect square. Now, a perfect square would be like 1, 4, 9, 16, all that good stuff. So an even number or a perfect square. So the even numbers are here. The perfect squares are here. That means 4 counts both times, but we don't really care. We're only allowed to use it once. But anyway, if you look, you'll find out that 3 of the 4 options are either even numbers or perfect squares. So that would be 3 out of 4, otherwise known as 75%. A prime number. A prime number is a number that is only divisible by 1 and itself. So that would be something like this: 2, 3, 5, 7, 11, that sort of thing. So in this particular case, I will use a different color because I guess I've drawn too much. 2 is a prime number, 5 is a prime number, 4 and 9 are not prime numbers. So we're going to go back to the 1 out of 2, which would be 50%. And we're almost done with this section here. A 2-digit number. Well, none of them are 2-digit numbers. There is a 0% chance of that happening. All right. State whether A and B are independent or dependent. All right. A single coin is tossed twice. And keep these problems in mind for 7 and 8, because you only have a couple problems you're going to have to do on your own, but they are all about independent and dependent. A single coin is tossed twice. Event A is having the coin land heads up on the first toss, and event B is tails on the second toss. So remember, coins are independent events. It's not like one coin knows what the other coin is thinking. Okay? Number 8, 2 cards are drawn from a standard 52 card deck. The first card is not placed back in the deck before the second card is drawn. Well, wait a second. If you didn't put the card back, then that means the second draw is going to look a little different from the first. So those are dependent events. So your second card depends on what you drew for the first card. If you drew the Queen of Hearts on your first draw and then you didn't put it back, that means you can't draw it for the second one. So your second drawing depends on the first one. Okay. All right, number 9. All right, number 9. Now this one's a little bit tricky. They're telling you the probability of the first thing happening is 0.5, and the probability of both things happening together is 0.3. What is the probability of the second thing? Now, in case you forgot, whenever you're dealing with just an AND problem, the probability of A and B, now that was the symbol for the intersection, in case you forgot, all you have to do is multiply the two numbers together. So the probability of the first thing happening was 0.5. Now this is where people get mixed up. The probability of both happening is 0.3. They want you to work backwards and figure out the probability of the second thing happening. So basically, I don't know this number, and I have to go back and find it. I think the best way to do it, I mean, it's not like you didn't take algebra, call it x. And that would give you, if we just set up the equation the way we're used to seeing it, 0.5x equals 0.3. So how would you do that? Well, I mean, I know it's got decimals and it bothers some people, but the truth is it's really just going to be treated like a one-step equation. So divide both sides by 0.5. By the way, this question is another one that got pulled directly off of end of course exam style work. So maybe it doesn't matter right now, but that's where the concept came from. Long story short, 0.3 divided by 0.5. Don't overthink that. It's the same as 3 over 5. If you moved the decimal over 1 on top and then over 1 on the bottom, then you would get 3 over 5. Now you could write that 3 different ways. 3 over 5 is good. 0.6 is good. 60% is good. It's all good. All right. We'll do 2 more, and then I'm going to have you do the independent-dependent problems, and then you can try for some extra points on number 14. All right, you flipped a coin and you rolled one number cube. Sometimes, to be politically correct, they call them number cubes instead of dice because they think that using the phrase dice or the word dice will promote gambling. Don't even get me started on this. Sometimes political correctness just drives me crazy, but that's another story for another day. What is the probability of heads and less than 3? So you've got the probability of flipping a coin and getting heads, which is 1/2. We've already talked about that. The probability of rolling the dice and getting a number less than 3. Well, out of the 6 options when you roll the dice, 2 of them are less than 3. It could be a 1 or a 2. All right, so you multiply those numbers together. Whenever you see an AND problem, all you do is multiply, and you get 2/12, which if you had reduced early, you wouldn't have to reduce later on, but either way, you get a probability of 1/6. All right, what is the probability of getting heads or a number less than 3? So now this OR problem was the trick where you add the probabilities and then you subtract the probability of both happening. Okay, so now you basically take the 3 numbers that we already came up with and you work with them in a different way. Now, just to throw this out here, I know it's sort of a 6th grade thing, but a lot of kids forget. You can't add or subtract unless you have a common denominator. So that 1/2 I am going to change, and I'm going to call it 3/6 because it still means 1/2, and I will have a common denominator. So 3/6 plus 2/6 minus 1/6 would be 4/6, which I would reduce, and I would just call 2/3. So there is a 2 out of 3 chance that you will get, you'll flip heads or roll the dice and get something less than 3. All right, the last problem we're going to do together is called a two-way table. It is one of my least favorite types of problem, but the state of Ohio really likes it, so I keep teaching it. All right, 300 people attended a kids event and 1 person won the grand prize. The probability of selecting a child, given that the winner is female, is 0.6. Complete the two-way table. All right, so here we go with that word given again. So we'll see how that impacts our two-way table here as we go. Now, a two-way table basically means that every row and every column have to add up to the correct number. So if we know that there are 100 males attending the kids event and 300 total people, that means 200 of the people had to be female. If we know that the total number of adults was 120 and the total number of people was 300, that means the total number of children needs to be 180. So you're really just subtracting 120 from 300 to get what you're looking for. All right, now, to get the remainder of the information, you have to use the second sentence. The probability of selecting a child, given that the winner is female, is 0.6. Now, that word given here is the key. Given that the winner is female, the probability of selecting a child is 0.6, which means 60% of the females in the audience are female children. So if you take the number of children in the audience and you multiply by 0.6, you will get the number of female children. And as soon as you get one more number, everything else takes care of itself. So here's what we're going to do. We are going to say, hey, there are 200 female members of the audience, and of those 200, 60% of them are kids. So 200 times 0.6 would be 120. Now that doesn't seem like it's a huge deal, but as soon as you get that number, every other number takes care of itself. Because now we know that there are 80 female adults, and then we have to make every row and every column add up to the correct number, which is why now we can just put a 40 there, and we can put a 60 there. Two-way tables are pretty weird, but again, it's something that a lot of states have been adding to their testing, and so we might as well be ready for it. All right, so your directions, just in case you're a visual person. I want you to complete number 12 on your own and number 13 on your own. Number 14 is extra points. We will say 3. So if you are able to get number 14 right, then you will get 23 out of 20 on this assignment. All right, thanks for doing your math today. Appreciate your time. I hope you're taking care of yourself, taking care of each other, and I will see you next time. Take care.